Hello, here's Johannes Kade from IPMS. We will start our webinar in the next few seconds. So, it's 2 o'clock. Ladies and gentlemen, welcome to our webinar. My name is Johannes Kade and I'm Business Development Manager at Fraunhofer IPMS in Dresden. The title of our webinar today is MEMS Technologies for Vehicle Environment Detection, and it should give you an overview about the current technologies and the research activities at IPMS. I also welcome Mr. Jörg Amelung from IPMS. He is physicist and he has more than 20 years experiences in the development of MEMS device technologies inside of the Fraunhofer Society. After founding the research fab Microelectronic Germany, he is now heading a new department, active micromechanical systems, to develop sensor systems for innovative applications. I'm looking forward to Jörg's interesting presentation, and please be so kind, if you have any question, note them at the side of the webinar application. Jörg, now it's your turn.
Thanks, Johannes, for the kind introduction, and also from my side, a kind welcome here at the webinar. I want to give you an overview about our MEMS technologies for vehicle environment detection and why it's an interesting future application. First of all, let's start from that side. Autonomous vehicles need, of course, a precise environmental detection. It could be in the field of autonomous guided vehicle in the industry. Of course, autonomous driving and cars is important. Drones are important, or in the agriculture. All these vehicles need very good sensors for the surrounding. And this is the reason why such sensors have actually a big boom. The question mark is how we can integrate that. And when you see the classical sensors, and here I want to present a test car for that. And you see a lot of sensors for the surrounding, but you see that they are a little bit too bulky. It looks not very good. And in a lot of ways, is it too costly to produce them. And additionally, we are in the field of car manufacturing. We need also very good robustness, and this is also very important when you have a strong indication from the road to the sensor. Microsystems could be their solution, and I want to show you two examples and what we do there. First of all, for vehicle environment recognition, we need a safe sensor coverage. Actually, solutions for the detection could be subdivided in 4 sections. A lot of systems use cameras, radar, LiDAR, and ultrasonic. And these are the main detection sensors which are used in autonomous vehicles. And now is the question mark, why I need which sensor at which place. The important thing is there that all of these sensors has some advantages and some disadvantages. To have a safe detection, you need at least 2 independent physical detection modes to be sure that you have no glitch or wrong detection of your surrounding. This is very important, especially when you go from only assistance system to really autonomous operation, because in that case you cannot have the influence by the driver itself. So from that side, it's very important to have at least 2 physical detection modes. Main challenges for such sensors are in the range of cost reduction, range when you have a long range detection, robustness, and also dimensions. to integrate this in a smooth way into the vehicle. Let's start with one application that called solid state LiDAR. LiDAR stands for light detection and ranging. And there's a very interesting principle, which is actually really a boom. Go to that. We are discussing here actually about solid state LiDAR, so not a mechanical LiDAR. A solid state LiDAR allows a cost-efficient solution for safe detection in the surrounding. There are different approaches for LiDAR. One is MEMS-based scanning LiDAR, which will be the topic from today, but also flash LiDAR is an important aspect. What is the principle? The principle is that you have a laser diode or laser source, which make a light which go over a modulation system, which in our case is a MEMS scanner, and this scans the surrounding. So the light is illuminating the surrounding, and the backlight will be detected in high, but so in power, and additionally by a time of flight mode. So we measure the time of flight to the system. Additionally, besides the different approaches, there are also different wavelengths which will be used. 905 nanometer to 940 nanometer is well known, but also 1550 nanometer is very important because of eye safety issues. You can generate more light to illuminate the whole scene. We are mostly inside the MEMS-based scanning LiDAR, and I want to show this. Besides that, we have a strong cooperation inside the research fab Microelectronic Germany, which not only covers the MEMS part, but also covers the whole value chain for LiDAR in a certain way. So for 905 nanometer and for 1550 nanometer. And you see it here. We are actually here at the IPMS more dealing in the field of beam steering, so the really MEMS-based LiDAR. And this I want to show you more now in detail. The MEMS-based LiDAR concept, in a very general way, you see here, you have light source which go over an optics directly on the MEMS systems. These MEMS mirrors can be one or up to several MEMS mirrors, and then you illuminate the surrounding and detect the incoming light additionally. And to optimize both ways is an important issue to have a safe and also a very robust detection. We use here at the IPMS a very special microscanner mirror principle, which is a little bit unique. It was developed here. So we have a resonant driving principle by directly having electrostatic evaluation of the mirror, and so you get a tilting mirror which have a resonant scanning of a certain angular dependence. And you can see here how it works. The resonant driving principle is driven by interdigital structures and allows a very low driving voltage for large deflections. So the interdigital structures generate a wildly directly tilting of the mirror, and based on that you can scan the whole scene by directly one mirror deflection. One interesting thing you can also do, not a so-called resonant principle where you have a laser view figure which scans in a directly time manner. You can also use a special quasi-static mode, and this quasi-static mode generates a complete independent or better scanning of certain angles more dense than the others. This is very important when you want to have different solutions in different areas of your scene, so that you scan a certain area in a more detailed way than another one. To optimize such MEMS scanner, we have a lot of things to take into account. It comes from the dynamic deformation over shock resistance, some reduced cost, of course, quality issues, frequencies are important, and last but not least, we need also to have a good field of view, a large deflection. And I want to show you now some aspects from the system side, which we developed here at the IPMS. Let's start with a special application for this quasi-static mode. You see it here. The idea is to have a Fourier application so that you have a sharp area which you scan more into detail than the other ones. Like in the eye, where the Fourier is really the point of the sharpest seeing. And for that, we need a 2D MEMS scanner for fast adaptive scanning. And this was a development issue here in this field. The idea was to detect in an industrial surrounding really some object and measure also the distance to that. So here you can see how it looks like. So for that application, we need more than one mirror. We have a lot of mirrors inside, up to 5. And based on that, we have an effective aperture of 5 millimeter in square. And this gives you a field of view over than 60 degrees, which is very good in that field. Very important was the optical resolution, about 1 milliwatt. And the laser was at 1550 nanometer with a peak power of 1.5 kilowatt. Important was really also the accuracy. Is an industrial solution. We need about 5 millimeter for 1 sigma in 7.5 meter distance. And for that, to achieve that, we use a very clever configuration, what you see now in the next foil. Here you can see the scan head. The scan head has several mirrors and photodiodes for the backside for the detection inside. And based on that, you can detect directly very sharp in a certain distance objects with this Fourier point. Here you can see an experimental result is a 3D image in 6.5 meter distance. And you see a lot of directly objects in this field. And based on that, we can also demonstrate also this special operation point for sharp points to detect more into detail. So it was designed as a demonstrator for such industrial applications. This is one possibility. What is, of course, very important when you go to vehicle detection is the robustness. Reliability topics are one of the main issues which was often asked us. What is regarding the robustness? And I want to explain some parts of this reliability topics to you. When we think about reliability, we have a lot of different parts we have to take into account. The temperature, the humidity, dust, pressure, fatigue, vibration, and shock. When we subdivide that, we have on one side the temperature and the robustness of the material itself. There we have a very good opportunity because we have single crystalline silicon for the MEMS mirror. And based on that, we have a low coefficient of thermal expansion and additionally a high stability. So we can show our millions of cycles that our system is stable without reduction of the stability. On the other side, we have the parts temperature, humidity, dust, and pressure. This is mainly package dependent, so it's a part of the integration option of our system. Last but not least, and this was a question point when we go to really vehicles, what's regarding vibration and shock? Because we have here a mass which is moved, will be moved. And based on that, it was a question mark, is the MEMS material and the design in a certain way and robust enough for the vibration. And I will show this. How we test this? We have different standards for vibration reliability testing. It's related a little bit to the application. You see an overview. It goes from agriculture to military. Our dedication was automotive destruction vibration tests, LV124. And this is an idea to qualify our system against the automotive standard. And you see here on the right side the frequency and spectral density of the acceleration at the different for the different standards, and the red one was the target point. So what we done in the first stage, we tested it in-house, and you see here how it's looked like. Here are the highest loads between 3 Hertz and 100 Hertz. And additionally, you see here some issues regarding the mounting itself. There's one point a little bit above 1000 Hertz, about 1 kilohertz. And from that side, we had the wide power spectral, and based on that, we could show that our system is stable. Additionally, we done a directly vibration load during some bumpers to roads testing in Dresden, and I can say in a quite big sense that we have some roads which have some really bumped area, and you see here how it looks like, and also there our scanner survived in a good way, but you see also that the test, the reliability standard test, the LV124, is above the really hard roads here in Dresden. Nevertheless, our sensor survived in a very good way, and this was a good point of starting together with our industrial partner if this is really in a good shape to go into the next stage, and this would be then the integration into a real system. And I'm a little bit proud of that we can now say it, that we work now over several years together with a company who can show this then into a product. So as the starting point, the vibration load can withstand with the sensor and also the directly testing. And this company calls AI, it's located in US and is one of the highest growing company in this field. And from that side, you see here some of the features of our of the actual prototype, which was done by this company. The features are very, very hard. So from that side, you can have up to 4 million points per second with a resolution better than 0.1 degree. Additionally, we have the possibility to classify objects 10 or 20 times more accurate than with an only camera model. There is also a detection inside for small, low reflective objects in the distance up to 120 meters. Interesting is that we can put our MEMS system there inside, and it works at 1550 nanometer wavelengths. And this is a really breakthrough that it works like that. Additionally, it's combined with as an option with a camera. And it was an interesting point. Could we solve all of the issues for our customer? And now I can say, yes, we could it. And here I only want to give a statement from our partner of AI that the LiDAR industry struggled an often time if the solid state LiDAR has enough performance to achieve on long range the high resolution. and it's directly done with our MEMS-based LiDAR. And so they could show that with this micro MEMS, which is only a one mirror system, you can detect in a resolution way as you have it with an FMCV LiDAR or other more sophisticated systems. So for us, it's a really breakthrough. And I said, together with our colleagues, we are very proud to say now that we solve the main issues in this field. And this is good background for the next developments. The next part I want to show are in the field of ultrasonic transducers, a second possibility to detect the in-vehicle surrounding. What could be the real application for something in the autonomous vehicle range? The very normal working issue is in the field of parking sensors or distance measurement. Additionally, we can also use ultrasonic in the field of gesture recognition inside of the car. So this is a second order application field we can look around. Why we now can use here microsystems. For the normal distance monitoring that's done by the classical sensors, the main part could be in the field of the side detection. So to the side, you have some issues to detect in a range of a blind spot coverage or to detect bicycles directly nearby. And up to now, this is done with some sensors really at the low side of the car. The best possibility would be to have it integrated in the mirrors, in the rear mirrors. Unfortunately, you see it there on the picture. Such ultrasonic sensors are a little bit bulky. It looks not very good. So the question mark is how we can integrate that there without having too high or too main dimensions. We are working in the ultrasonic application area with different technologies. You see it here. It starts from the lowest kilohertz range up to megahertz range. In the megahertz range, we use CMUTs, capacitive micro-machined ultrasonic transducers. In the low frequency, we have a different principle I want to show you now. I also can measure. We are there in close cooperation also with other institutes inside of the FMD, for example, the ISIT in Itzehoe, which use a different principle. What we do is a very special and here developed driving system. It calls Nano eDrive. You see it on the left side. The Nano eDrive has some opportunities because you have a very strong force, and additionally you can use the whole volume of the MEMS for generating of the sound. So combination of both generate a low frequency and powerful device. How it works? We generate with a special structure on top of a bar. We generate a special force which generate then a banding of the whole system. Interesting there is that the force will be added over the whole bar distance. Based on that, we can generate with several forces or with low deflection, a very large deflection of the whole bar system. When we do it like that, then we generate a compressive stress inside the whole bar, and this go then downwards as a tilted point. You can also make it in a different way. You see it here that the structure is inverse, and based on that you can also generate an upwards deflection. This could be done in the Y direction, so out of the plane, but also in plane of the wafer, of the silicon itself. And this has a very strong advantage I can show directly on the next slide. So based on that, you generate really a bar which can be deflected much stronger, factor of 100 stronger or higher than the really deflection. And based on that, we can generate when we do it in an in-plane, a really acoustic device. You see it here. You see it on the right side. Based on such columns, we can generate sound inside of these channels, which has a very strong signal power amplitude. So it's a very high power acoustic device. And additionally, of course, it's very small. And this, as a compact, high efficient device, is very useful, of course, to detect the surrounding. Of course, based on the long of the distance of the bars and other things, generate then the frequency of the system. And how it looks then there, I want to show here inside the video. You see here all of these actuators, and the actuators then can move from one side to the other side. And based on that, you make compressed air in the whole frequency range. And this is a very compact field. We can really put this together into arrays. Here there's, of course, a very strong array. And together, we generate then very powerful sound pressure outside. This can be then integrated into a very small package together with the driving electrode and a good package. We can generate a very compact ultrasonic transducer. How it looks now from the actual status, you can see it here. Here you can see a system which has a transducer inside and some microphone structures in the outer side. And we generated then a really sound pressure up to 100 dB. And this is very useful, of course, to detect. And this, we can also demonstrate this to make a measurement in the distance field for gesture detection, or, as I said, for the surrounding of vehicles. And this is a starting point where we are looking for partners to develop now the next stage, to develop here some really industrial solution for have very compact and very powerful ultrasonic sensors. As a conclusion, we have opportunities to make an effective environment detection, and this is essential for the safe operation of autonomous vehicles. Traditional sensors solutions are costly and also bulky, and so from that side, it's not the right solution really for making in a mass production. MEMS-based sensor could solve several issues for this future autonomous vehicles, and I wanted to show to you that it's also robust in operation, has small dimensions, and has a lower cost solution opportunity. The Fraunhofer IPMS offers in this field innovative solutions for LiDAR and ultrasonic sensor systems. And together with our partners in the research fab of Microelectronics Germany, we could also offer complete sensor solutions. So we can design from you over the whole value chain, from the light source till the detection unit and the integration. We can solve your problem for the next generation of environmental detection. And with this conclusion, I want to close my presentation and thank you for your attention. And now I'm open for some questions from your side, of course.
Okay. Jörg, many thanks for your excellent and great presentation. Nearby the end of the webinar, there are some question from the audience. I have a look in my desk. Just a second. The very first question: what are the next challenges for environmental detection in the near future? And
Yeah,
what is the luck? And additional, what is the luck for a complete application?
Mhm. From my side, I would say there are a lot of opportunities still ongoing about the integration of such detection modes into real applications. So the integration really in a surrounding that it works in a reliable way over several years together with other sensors in a sensors fusion manner is one of the most challenges for the future. And of course, we are at the beginning of such sensor fusion. As I mentioned it, we need more than one physical detection mode to be really safe that not all of the cars or all of the autonomous vehicle has based on error has some damages or make an accident. So that is, I think, to have a safe operation over all of the entire sceneries is one of the most challenging part for the future.
Thank you. And what do you think? What are concepts for reliability of complete systems for the use in automotive sector? I think you have shown that we have very reliable single devices, sensors and actors and actuators, but the reliability is necessary for the complete systems. And that means I could imagine that we need much more integration for the reliability.
Yeah, that's right. That's right. We need much more reliability for the whole system, especially when we have here a really, for example, for LiDAR, when we have a very precise measurement of the surrounding. It's of course very important that all of the optics, all of the detectors in a certain way is robust against all of the frequencies, which accelerations, which can come to the system itself. And so the integration of that is not so easy as it seems, because we are discussing here about precise optics and not about some illumination of the surrounding. So from that side, this is still an open issue, I think, to solve in an integration way.
Okay, thank you. Mr. Philip Robert has two questions. Regarding slide 31, he asked, the transducer is used for ultrasound generation or sound or loudspeakers?
Both. We based on the principle, we can use it for sound generation, of course. Then it's for in-ear loudspeaker, for example, a certain way. But we have the opportunity, we can cover frequencies up to 300 kilohertz. So you are also in the field of surrounding detection for the surrounding more far away. 40 kilohertz and 80 kilohertz is very common. For gesture recognition, then it's about 300 kilohertz. It's more common.
Thank you. And the same Mr. Philip Robert asks, is it in capacitive or in piezoelectric actuation?
Or here of the NAD, it's an electrostatic actuation. It's electrostatic forces between the electrodes in the top way and the common electrodes, and based on that you generate the force. There's no piezoelectric inside. That's very good, because in that way you have a direct actuation and not based on piezoelectric some material issues inside.
Okay. Are there any other questions from the applications? If there are not, ladies and gentlemen, it was a great pleasure for us to meet you in our webinar. I hope you got a good overview about the IPMS development activities, and we could make you interested in research cooperations with IPMS. And we hope to meet you again in another webinar from IPMS announced at our website. The next webinar will happen on the 16th of July at 14 o'clock. And the title will be Low Frequency MEMS Ultrasound Transducers. I hope we will see you again. And that's all for today. I wish you a nice day and a good time. Bye-bye.